your picture, but this is the Beckman 890C spinning cup liquid phase protein sequencer that the Gobin's laboratory had. Spinning cup, well, actually, if you look at this portion, there's a cup rotating, and aqueous liquid, sorry, I'm not used to this one. Aqueous liquid film is formed here due to centrifugal forces, and then organic solvent gets delivered here, and organic solvents skim surface of an aqueous phase, delivering reagents and then collecting products, and then gets siphoned off to test tubes. This is a liquid phase sequencer, automatic sequencer designed for Edman degradation. And Gobin's group, this is the first amino acid sequencing project of Gobin's group in MIT. These arrows indicates where Edman degradation can decipher, but there are areas that this Edman degradation cannot cover. And in chemistry department, Klaus Biemann came to us, and he said he's going to sequence any protein with mass spectrometry. And Gobin, I think he told me later, but Biemann says that he only needs a few milligrams of proteins. I think we ended up supplying Klaus Biemann's group a few hundred kilograms of bacteriorhodopsin. It was culturing bacteriorhodopsin. Chris Clay cultured so much that our servo centrifuge was clogged up with sodium chloride crystals. We take out the mortar, put it in water, and then dissolve the salt, and then put it back again, and that sort of things. But anyway, mass spec was used to cover the area that Edman degradation cannot cover. Wait a minute. However, Klaus Biemann's group started sequencing proteins with mass spec. At the beginning, it was gas chromatography mass spectrometry, GCMS. The first one was 1976, 44 amino acid monelin. And then second happens to be bacteriorhodopsin, 248 amino acids. And if you look at Klaus Biemann's reviews, there are several reviews. He always mentions about and thanks Gobin Khorana for providing bacteriorhodopsin. But then he went on to sequence E. coli alanine tRNA synthesis. I think Data-Zo's name was mentioned in this description. He was somehow instrumental in providing, I think, protein samples. But then in 1981, first atom bombardment MS came out, so GCMS was no longer available. These days, we use MALDI or matrix-assisted laser desorption ionization method is used for protein sequencing. But actually, it was in competition with a Russian group. And so there were areas that mass spec couldn't cover. And indeed, in fact, we got help from a solid phase sequencing company called Cytochrome. And because I used to live in Brookline, and this company was in Watertown. So when I commute, I kind of became messenger boy and delivered the peptide and delivered back the result and that sort of things several times. Alex is being very kind person, and I think he did sequencing. He helped us sequencing free, I think. But then Gobin eventually bought solid phase sequencer from Alex. Also, Edman liquid phase sequencer was used to locate the retinol position. I was the operator of a sequencing machine after Gerhard Garber left. One important thing that I want to mention is that we kind of developed organic solvent system. This is gel permeation, gel filtration chromatography, ethanol, formic acid, 4 volume of ethanol and formic acid 1. We leave it for 1 week, and eventually ethyl formate is formed and equilibrated. So it must be a mixture of these four components. This was very great solvent for solubilizing membrane proteins, very hydrophobic proteins. Now getting into main topics, I'm going to talk about the photocross-linking sequencing that I did in Gobin's group, because this hasn't been talked much. Gobin's group developed many phospholipids with photoactivatable probes, but we ended up using carbene generator. Carbene is carbon losing 2 covalent bonds. And this has a capacity to associate with organic compounds like hexane, CH insertion, for instance, upon photoactivation. Another one was diazo trifluoropropionyl group. Dr. Chitar Gupta over there synthesized this compound, labeled this compound with C14. And I didn't know until a few hours ago that when he synthesized these radioactive compounds, the firefighters and radiation protection officers were standing by just in case explosion happens, because he used radioactive phosgene. So I didn't know that until today. Diazo, okay. So it was a very dangerous project, to say least. But unfortunately, this diazo group got reduced by dithiothreatol or beta-mercaptoethanol reductants. And so I looked for the protein that doesn't have any cysteine for sequencing project, and I found Cytochrome B5 in Dayhoff's protein atlas. It has a C-terminal hydrophobic domain, which gets, usually it's octamer aggregate, but if you mix this with phospholipid vesicles, it spontaneously inserts into these vesicles. If you have other type of membrane like mitochondria, then this moves to another vesicles. So it has a capacity to transfer between vesicles. And if you apply carboxypeptidase, then it eventually loses the ability to bind to phospholipid vesicles. These are called loose binding form. However, if you treat this preparation with dilute cholic acid or sonication, then somehow the samples become no longer transferable, and carboxypeptidase doesn't digest, it stays on the membrane. So it's called tight binding form. And about this square is supposed to be hydrophobic sequencing. Govin's second sequence project was sequencing of this hydrophobic region of Cytochrome B5, which was published in 1980. So we tried to see the membrane embedded portion using phospholipid containing photoactivatable probes. And to do that, we checked into the conditions. Finally, we ended up using an arc lamp, 1,000 watts mercury xenon arc lamp, but we pass the light through the monochromator, and then to make sure that we don't get any stray lights into it, we purify the light with filter cutting of 345 and 360. The sample, actually, there is a cuvette here. The light passes through, but the sample is covered with water jacket to cool it down, and also the sample was under strict nitrogen. If you shine the protein with oxygen in it, without any photoprobes, these lights will somehow make aggregates of your proteins. The oxygen causes activation of maybe tryptophan, something like that. And it's known that you have to shine the light to protein without oxygen. Gupta's reagent, it took 40 minutes. Radha's reagent, the top one, took 2 minutes. Nevertheless, Radha Krishnan and Dr. Gupta both made the vesicles and photo-irradiated their samples and measured the point of distribution of crosslinks to opposite strand using mass spec, and the beautiful pattern of bell shape was, at least this is a part not complete, but was obtained. If you label here with a deuterium and measure the distribution of these deuteriums, it scatters around like this. So it's reflecting a similar type of distribution. It looks like having a benzene here, phenol group here doesn't interfere the movement. So I did the cross-linking using these conditions just to make sure I added the tryptophan 25 millimolar into the solution too, to avoid tryptophan damage. This is a gel permeation chromatography, phospholipid monomer, phospholipid dimer, cross-linked cytochrome B5, but cytochrome B5 also got oligomerized, likely to be oligomerized at the hydrophilic portion having a heme inside. And this cross-linked portion was treated with alkaline and acid. There were a huge amount of, or more than half of acid label, alkali label, cross-linked product. And these label products cannot be analyzed by Edman degradation or stepwise sequencing, because stepwise sequencing requires acid phase and alkali phase. So by stripping off unstable groups and then applying them to the sequencer, but liquid phase sequencer couldn't retain the cross-linked peptides. It just went to organic solvent. So I had to use solid phase sequencer. This is a solid phase sequencer that Govin bought. Also later on, Alex Bonner, I was kind of involved, but changed this to DNA synthesizer too, using Marv Crothers reagents. And also, I had to improve the coupling yield. Aminopropyl grass seeds, control poor grass seeds, didn't couple very well, only 5% or so. So we, with Gupta's suggestion, we lowered the pK of amino groups by having a allyl group here. And this new grass seeds coupled more than 50%. Using this, also the sequencer has to be tuned up to get higher repetitive yield. Edman degradation, each step is not 100%. It could go up to 97%, but not more. And it's quite difficult to get up to 97%. I changed the tubings and lots of things, programs, etc., to get to 95% yield. So this was original cross-linked product coming out of machine. I corrected the value for repetitive yield in dotted line, and these are the distribution of cross-linked area, starting from saline here, saline here, saline here, saline here. Many times it was the same. So we sort of with that result, we kind of speculated the membrane-bended area of loose binding form, and this was figure 7 of my JBC paper, first paper. This was taken up by textbook. It says permission of author, but they never asked our permission. So tight binding form. I did the sequencing same, but the sequencing area, cross-linked area was somewhat different. It started from this setting here, 3 residues into the hydrophobic area. These are very hydrophobic peptides. And so difference is loose binding form is wider, tight binding form is a little bit more compact. And to cut the story short, to answer the question, what is a form of C-terminal end? I created asymmetrically distributed vesicles, having C14 in outer leaflet only, using phospholipid exchange protein of Carl Oates. And then also I made a tritium-labeled phospholipid predominant in inner leaflet, taking out the outer leaflet radioactive protein, diluting out the outer leaflet phospholipid, photo-labeled phospholipid by adding an acceptor here. And cross-linked separately and mix them together and used chemicals to get the fragment, and CO ratio clearly showed higher CO ratio at the N-terminal side with a gradient of going down, which is consistent with transmembrane configuration. Now, if you look at the protein sequence of this hydrophobic region, there's a proline here. And proline has a very low threshold of cis and transform threshold. So my speculation was that loose binding form has 2 helices in outer leaflet with proline in cis form, but then if you sonicate or if you treat it with dilute detergent, then this becomes transform, and the helix comes much more tightly, and so extra cross-links that was required is no longer cross-linked. And this is the farthest that I could get. Gobin asked me to make CPK model whether the speculation fits, and it does fit quite nicely. I'm out of time, I think. So recently, I'm doing proteomics using multi-topmass and that sort of things, but I'm not going to get into this, except there are, well, I did put myself in genome research, molecular biology at one time, but membrane protein analysis is very difficult, tedious. Easy things get done very quickly. So for young people, don't put yourself in easy things because you lose a job in 10 years' time or something like that. Things will change very quickly. Always try to work with important projects, but difficult ones. This is an example of, if I do analyze the proteomics of many interesting samples, like this one, cardiosphere, it's cardiac stem cells. We see huge amount of heat shock proteins. They are more than half of the expressed proteins. So, and if I analyze, this is a heat shock protein with this different charges. The antibody against phosphotyrosine, antibody against acetylated lysine, those will show you that these are chemically modified materials. There are huge area that needs to be analyzed of post-translational modification. And that's something that we have to, heat shock protein, it must be responding to the environmental change or some condition. These are the areas that will be, I hope, will be flourishing in 20 years' time, something like that. I associate myself with Nobel laureate of physiology and medicine. Osumi actually happens to be, he got his Nobel Prize with autophagy last year. He was 3 years senior than me. For my undergraduate thesis, he actually was a tutor. And then after Gobin, I moved to Center for Cancer Research as a staff scientist. Salvador Luria, director then, provided me machinery that I needed. And then basically I associated with Susumu Tonegawa. We discovered T cell receptor alpha chain, gamma chain, and gamma delta T cells. And then Phil Sharp succeeded Salvador Luria in 1985. He immediately came to me and asked me to open up a microchemical laboratory in cancer center. I used to produce 80 oligos per month provided. And I'm sure that that was quite helpful to become MIT biology department as #1 ranking in United States at that time. The important thing is that these people has very common character. They stick to something important. They are single-minded persons, but stubborn persons. They are persistent and never jumps around. So look for a great person who has insight, very consistent with the patients. Unfortunately, Tonega wasn't a patient person, but other people were very patient. But my Gobin used to say dead center focus, and that's what these people did. One thing, big advice, I associated with Gobin 6 years and Tonega with 7 years. That's a golden step for failure. I mean, one should get independent much earlier to grow. And association with great people for a long time is not that good. Thank you. Thank you very much for letting me talk all the stories.
Thank you very much for your very insightful pieces of advice. Does anyone have any comments? I know we're getting very late and this is a very historic talk, but does anyone have any comments? But if not, please join me to thank you once more for your wonderful talk. Okay, so I hand back to the organizers now.
Yeah. Thank you very much, everyone. We would now request all the delegates and the poster participants to please go to their posters as there will be evaluations, and then we will resume for dinner at 7:45. So we close the session now. Thank you very much.